Okay, so let's look at this problem. So the first thing, this should be like second nature. The first thing is we need to find the eigenpairs. So these have complex eigenvalues. So 1 plus 2i is an eigenvalue, and the corresponding eigenvector is 1 plus I and 2. Okay, this is the one that Wolfram alpha gives us. Okay, so there's also a second eigenvalue, an eigenvector, but it's just going to be complex conjugates. And remember, when we're dealing with the complex case, we want to look at this and use the fact that the real and imaginary parts of this function are going to be 1, linearly independent, and 2, solutions to this differential equation. And so the general solution is going to be a linear combination of the real and imaginary part of this. Okay, and so we're going to use Euler's formula, and so I can rewrite the exponential as e to the t times cosine 2t plus I sine 2t. So I've basically split the exponential part up into real and imaginary parts, and I'm going to split the vector into real and imaginary parts. Okay, and now the real part of this is going to be e to the t cosine of 2t times 1, 2 minus e to the t. Let me write it consistently with how I wrote the other one. Minus e to the t sine 2t times 1, 0, and the imaginary part is I e to the t times cosine of 2t 1, 0 plus e to the t sine of 2t 1, 2. Okay, so then this tells us that the general solution is just going to be a constant times the real part plus a constant times the imaginary part. So this is a e to the t times the vector cosine 2t minus sine 2t, and then the bottom is going to be 2 cosine 2t, now plus the imaginary part, or plus b times the imaginary part. Okay, and then this is going to be cosine 2t plus sine 2t, and then 2 sine 2t. Okay, and so this is the general solution to the corresponding, this is the general solution to the differential equation. I was going to say corresponding homogeneous equation, but this is a homogeneous equation to begin with. Okay, so that's all we have for this problem.